chemistry.
Really now.
All right, well, let's at least look at, I don't know how long I'm going to be here, so we'll look at 2, 4, and 5, the idea behind 2, 4, and 5, okay? I won't do the actual problems, so let's look at 2, 4, and 5 and figure out if we can figure out why they're difficult in preparation for your extra practice problems for tomorrow. 2 says, to burn a piece of wood, oxygen has to be added. And ash, carbon dioxide, and water are products of the burning process. Do you see in that first sentence that we have a chemical reaction? We start with something or some things, and we end with some things, right? So looking at this problem, what are the things we start with? Just read the first sentence. To burn a piece of wood, oxygen has to be added. So we start with wood and oxygen. To burn a piece of wood, oxygen has to be added. Ash, carbon dioxide, and water are the products of the burning process. Ash, carbon dioxide, and water are the products. This side of the reaction arrow, these are the reactants, and this side are the products. So, to burn a piece of wood, oxygen has to be added. Ash, carbon dioxide, and water are products of the burning process. If, and then it goes through and gives you different masses, right? It says if there's a certain amount of oxygen, is used to burn a piece of wood, then what's the mass of the wood if, and we're given the mass of all 3 of those things. Right? For wood to burn, you need to add oxygen. The product of the combustion, the reaction, is ash, carbon dioxide, and water. I've been given the mass of the oxygen, the mass of the ash, the mass of the carbon dioxide, and the mass of the water. The question is, what's the mass of the wood? What is the law that's being used here?
Conservation of mass.
Okay. Law of conservation of mass would say that the sum of the mass of the reactants is equal to the sum of the mass of the products. Right? So, let's say that we had a formula. A plus B equals C plus D plus E. A equals what?
Subtract B.
And I'm going to subtract B from both sides. And so A is equal to C plus D plus E minus B. This is A, B, C, D, E. So I'm going to add the mass of my products. Subtract. Excuse me. We've got oxygen, not wood. So I'm going to subtract the mass of the wood is equal to the mass of the products of reaction minus the mass of the oxygen, which is one of the reactants, which I knew. Okay. So what was the difficult part about this question? Since this was the tied for the lead in the most difficult questions you had, what made this so difficult? I'm not, this isn't a belittling question. I really want to hear what was what was lacking? Why was this so difficult for you?
I just didn't know what to do.
I didn't do it right.
Okay. So you didn't, first of all, did you not understand that this was a reaction question? Don't know, okay.
It's just different learning how to solve for a reaction instead, but it makes sense in hindsight.
Did the concept that the mass of the reactants equals the mass of the products? Does that make sense to you, that idea? The law of conservation of mass, or the law of mass conservation. So if we start, and this kind of a problem is going to be something that you do in your sleep because it's going to be so fundamental to chemistry that you don't even think about it. It's just, I used to say it's intuitively obvious to the most casual observer that that's what you do. Right? So we've got wood and oxygen that react together to produce ash, carbon dioxide, and water. One way you need to approach all of these problems is to set up, first of all, be able to set up the reaction. To be able to look at the word problem and write the math problem. For those of you that had difficulty in word problems in math, this is a word problem for math. Again, wood plus oxygen, where do we get that from? Well, a piece of wood, to burn a piece of wood, oxygen has to be added. Wood and oxygen. Oxygen has to be added. Ash, carbon dioxide, and water are the products of the burning process. So in chemistry, we have this reaction arrow, and it takes us from the reactants to the products. Now later on, you're going to find out there are reversible reactions that go both ways. But for right now, you look at the reaction arrow and says, I have some things, and those things become something else through a process of reaction. The sum of the mass of the reactants. If you use Excel, you're used to this. All that means is the sum of all of the sum of all of the mass of all of the reactants. So the sum of the wood, the mass of the wood, and the sum of the mass of the oxygen equals the sum of the mass of the products. We talked about this quite a few days. That when you do a chemical reaction, you don't create any mass, you don't destroy any mass. You rearrange the mass. You put it together in different forms. But you can't destroy any of it, neither can you make any of it. The only person who makes and destroys ultimately is God himself. He's the only one that can make out of nothing something, and then take the something and make it into nothing. All we do is rearrange the something into look like something else. So we have the sum of the mass of the reactants, the sum of all of the stuff that makes up what we began with, and then at the end, we have not gained or lost any stuff, so the sum of all of the stuff in the product has to equal all the stuff we started with. So when you write our formula down, many times it's going to be, first of all, figure out one of the masses. And the mass of one side of the arrow has to equal the mass of the other side of the arrow. Then it's just a matter of what don't I know. Going through and checking off all the things that I know, and by elimination, find out what I don't know. And generally, that's the thing they're going to ask you to solve for. In this case, solve for the mass of the wood. Well, it's going to be the mass of everything I ended with, minus whatever I'm not looking for from here. In this case, the oxygen. I knew that. Subtract that from the sum over there, my remainder has to be what the wood is. If it wasn't the same, what would that mean? If, let's say I gave you the sum of the wood, and one side didn't equal the other, we wouldn't assume that, oh, guess what, we actually did lose something, or we actually did make something. The assumption would be, you know what, my system wasn't good enough to capture everything. There might have been something else included here that I didn't measure before I started, or there might have been something else produced here at the end that I didn't capture, that I didn't measure. The assumption would not be that I made or destroyed. The assumption would be I wasn't careful enough in my collection.
I think what's confusing about it is that the oxygen is then becomes part of the other it's not like a separate piece on the
Okay.
other side of the reactants, because that's what we're not used to.
All right, so on this side over here, we've got the oxygen. Where did the oxygen go? The symbol for oxygen is what? It's an O, right? We're going to find out later that oxygen is actually homonuclear diatomic, so it doesn't just float around as single oxygen atoms. They actually float around as oxygen molecules, two oxygens bonded together. So more technically be written O2. So we've got wood, and what is wood? Let's think about it. Part of this chapter is classifying matter, right? What is wood? Is it an element? Is it a compound? Does anybody know the chemical symbol for wood?
It's not,
Or the chemical formula for a molecule of wood? It's not, right? It's not a compound or an element, so it's not a pure substance. It must be a mixture. Is it a heterogeneous or a homogeneous mixture? I heard hetero. What about back there?
Homogeneous.
Come on. If you have a log, a piece of wood in front of you, can you see parts of it that are different from other pieces, other parts of it? Like, do you include the bark? Do you see the bands on the inside of the rings? Okay. The wood is actually a heterogeneous mixture, which means it has a lot of different chemicals inside of it. Okay, a lot of different things inside of it. What's the vast majority of what's inside a piece of wood, a log that you're about to burn? The vast majority of it is water. Okay. But what you can say is, okay, I've got wood and oxygen. I need oxygen for it to burn. You guys remember the fire triangle, right? The combustion triangle. Fuel, heat, and oxygen. So I need oxygen in here for this combustion to take place. There's oxygen, there's water trapped inside the wood, and when you first put a log onto the fire and it starts to smoke, it generally smokes white smoke, right? A lot of white smoke. What that is the wood, the water inside the wood turning into steam and being released. So you're seeing steam from the water that's captured inside of this wood. But what Will's point was is that maybe there's difficulty in seeing that the oxygen that you start with here is in the products as part of the carbon dioxide and as part of the water. That the oxygen here that was oxygen molecules here have now been broken apart and recombined with carbon and hydrogen. So the oxygen is still there. It's just, rather than being isolated molecules of oxygen, it's now in molecules of carbon dioxide and water. But in any case, this principle of the sum of the masses of the reactants is equal to the sum of the masses of the products should become very quickly second nature to you. To say we're looking for the mass of something, we're looking for how much of one thing. Well, I can find that out if I know the masses of everything else and just rearrange to solve for that one thing. In number 4, we take that principle of conservation of mass and we do an application. And number 4 is really just coming up with a perfect recipe. What is the perfect recipe is known as the balanced reaction formula. What's the balanced formula look like? So there's a certain amount in a certain reaction to make hydrogen peroxide. So I'm going to write the formula for hydrogen peroxide. You wouldn't be expected to know it necessarily yet. But I know there's a reaction because it says, in an experiment to making hydrogen peroxide, so where's the hydrogen peroxide going to go relative to that arrow?
right?
It's a product. An experiment to make. You're making it. It's what you're trying to produce. It's a product side. You're going to make hydrogen peroxide. A chemist mixes 40 grams of hydrogen 40 grams of oxygen. Now again, you wouldn't necessarily need to know that hydrogen and oxygen are homonuclear diatomics, but you would put hydrogen or oxygen beside it. It's really not that funny. Sorry. But 40 grams of hydrogen and 40 grams of oxygen to produce hydrogen peroxide. She finds that mixing 40 and 40 produces 42.6. In addition, there's a lot of hydrogen left over. How many grams of hydrogen should have been added to the 40 grams of oxygen so that there'd be no leftover hydrogen at the end of the experiment? So the first part was being able to write the reaction formula, the reaction equation. 40 grams of hydrogen reacts with 40 grams of oxygen to produce 42.6 grams of hydrogen peroxide and excess hydrogen. The question was, how much hydrogen should have been added to 40 grams of oxygen? There's two different ways that you could attack this, right? First one is pretty straightforward. It says, what's up for question? What does the question ask you that may be changed? It says, how many grams of hydrogen should you have added? Because there's excess hydrogen, right? So we've got too much hydrogen. So this is going to change, and this is locked in. 40 grams of oxygen. How much hydrogen should have been mixed with 40 grams of oxygen to make hydrogen peroxide? The fact that there was leftover hydrogen means there was too much before. So Tyler's right. I mean, it's pretty obvious here that if I've got 40 grams of this, how much of this do I need to make 42.6 grams of this? But to get there, you've got to mentally apply the same thing we just did with the wood and oxygen produces ash, carbon dioxide, and water. It's the mass here has to equal the mass here. 42.6 is made by adding 40 and 2.6. Now the other way to go about that would be to say 40 and 40 is 80. 80 equals 42.6 plus something. What is the something? In this case, the something would be 37.4. 37.4. Why? Because 42.6 and 37.4 equal 80. And so if the excess hydrogen here were 37.4, and I subtract 37.4 from 40, see, I'm going to end up with extra. Take the extra over here and subtract it from my original. The original minus the extra is how much I actually needed. I actually only needed 2.6 grams of hydrogen. It's kind of interesting if you note the formula. An H2 molecule and an O2 molecule produces an H2O2 molecule, right? But look at the mass here. For every hydrogen, how many oxygens are there? For every one, there's one. That's why it has the name hydrogen peroxide. For every hydrogen, there's one oxygen. Hydrogen peroxygen, or hydrogen peroxide. The hydrogen peroxide is the common name, just like H2O. The common name is water. Here the common name is hydrogen peroxide. What is its chemical name actually? What is its actual chemical name? H2O2. So start with, what kind of a molecule is it? Is it ionic or is it covalent?
Covalent.
Covalent because no metals. If it had a metal, and it would only have one metal, but if it had a metal, it would be ionic. It does not have a metal because hydrogen is the exception. Hydrogen should be if we're just looking at metals and nonmetals, hydrogen is to the right of the jagged line, right? So it only has nonmetals, so it's covalent. Because it's covalent, it does use the prefix paradigm. It does use mono, di, tri, tetra, so on. So, if I see this chemical formula, and I know that it's covalent, I know that I'm going to use the prefixes. And remember, the prefix comes from the element's suffix, or the subscript. The subscript here is a 2. So from table 2.1, it's 2.2. Either, I think it's 2.2. Table 2.2, what is the prefix that represents 2? Di. So I take, in this case, an H2, I'm going to write it, is said, if I take my subscript and I convert it to a prefix, di, then the name of the element. Dihydrogen. Okay. The second is, subscript is 2, so the prefix again is di. Now this is the trailing element, so it gets its ide name. Dioxide. Dihydrogen dioxide. 2 hydrogen, 2 oxygen. Do I have like a sign on my back or something? Is there anything written on my back? No? Okay, because every time I turn around and turn back, something's funny again. It's amazing. Laughs a million. Or this is funny. It's probably funny because it's so simple, right? So you can't believe we're actually spending time going over it. Mr. Baker, can we get to some chemistry instead of this stuff? Sorry, we need to press through this. So, dihydrogen dioxide. So, the excess of one, the excess of the hydrogen in this case, whatever was extra, could be eliminated from the initial reaction. So the necessary reaction would then modify this by removing the excess, by removing whatever was extra. Then you could check it real quickly by saying, okay, in this case I've got something plus 40.0 should equal 42.6. If it doesn't, check your math. I think probably the biggest issue for these 3 problems is just knowing how to take a word problem and set it up as a chemical equation, as a chemical reaction. So let's look at 5 real quickly, just the setup. In making calcium nitride, what part of the chemical formula can we write on the board? In making calcium nitride. Don't worry about the chemical formula, they're symbols.
What's on the left?
Start with the fact that, hey, I'm assuming there's going to be a chemical reaction here. There. Now I can start building it because I have the basics of a chemical reaction. This arrow tells me I started with something and I'm going to end with something. Moving this way. So my reactants, the things that are going to mix, are going to go on this side of the arrow. The things that come out of the reaction, they're going to go on this side of the arrow. And it says making calcium nitride. I'm going to go ahead and assume that I'm ending with calcium nitride. In making calcium nitride, 100 grams of calcium plus 100 grams of nitrogen makes 152.5 grams of the product. I'm going to make this arrow smaller so I can put it in front. 152.5 grams of calcium nitride with some leftover nitrogen. And you could have just written out nitrogen. How much nitrogen and calcium should be added together to make 1 kilogram of calcium nitride? So these 3 questions are related because this one is the first of the 3 steps. Number 2 was figure out the balanced equation. Number 4 was figure out the balanced equation with no leftovers. Number 5 is figure out how many multiples of the balanced equation you need. These are the 3 fundamental steps for the whole chapter of using this law of conservation of mass. So the first step of solving this problem is to first of all get your balanced reaction equation using the law of conservation of mass. How much extra nitrogen was there? Don't figure out the number. Tell me, what would you do? To figure out how much nitrogen was left over, what would you do?
Use it both sides.
So I would add up these two, add up all my reactants, and subtract, you're right? Add up all my reactants and subtract the product that I know. Because if I have 200 minus 152.5, the difference is going to tell me how much nitrogen was left over. So I figure out how much was left over, but I have to take the next step of writing what would the perfect recipe be, what would the balanced reaction be with no leftovers. So in this case, I take whatever my leftover nitrogen was and subtract it from this number to say how much would I actually need in order for 100 grams of calcium. See, there was no calcium left over. So remember the reaction engine? Calcium and nitrogen, it's reacting, it's making products until something runs out. It ran out of calcium, so there's no leftover, but it had extra nitrogen. So get rid of the extra by taking whatever the excess is and subtracting it from here, taking all of the other one, so 100 grams of calcium plus, and we can see from this, it's going to be 52.5 grams of nitrogen, would produce 152.5 grams of calcium nitride. Now I have the perfect recipe to make 152.5 grams. But I'm not asked to make 152.5 grams, I'm asked to make 1 kilogram. I'm not asked to make 1 batch. I'm asked to make multiple batches so that I end up with that many. So do you remember how to do that? What is the concept called? In your book, it's listed as the reaction multiple. Remember? If I have a recipe that makes a dozen cookies and I want to make 3 dozen cookies, what do? I triple it, right? I triple the batches. I make 3 batches. If I can make a dozen, and I'm trying to make 36, I take the number I'm trying to make, 36, divided by the recipe I have to make 12, and the result of that is 3. What's that tell me? I need to make 3 batches of 12 in order to have 36. Cupcakes, easy. Chemical reactions, still easy. Why? My multiple is going to be how much do I want to make? 1 kilogram, right? We get 1,000 grams. I have a recipe that'll make how much? 152.5. So when I do the math, when I divide 1,000 by 152.5, it's going to give me a number. And that number is my reaction multiple. That tells me how many batches of this do I need to make that much. If one batch makes 152.5, this number will tell me how many batches I need to make in order to end up with this much. Well, once I get that number, what do I do next? I take this reaction multiple and I multiply everything in my balance equation by that number. You know, if I have a recipe that makes a dozen cupcakes, and I want to make 3 dozen cupcakes, I say, well, my reaction multiple is 3. So if my original recipe called for 1 egg, I'm going to need 3 eggs. If my original recipe required 1.5 cups of flour, I'm going to need 4.5 cups of flour. I'm going to take everything in the recipe and multiply it by my multiple, my reaction multiple. So whatever this number is 6, 7, it's almost 7. It's a little bit less than 7. So let's say it's 6.7. Just throw that out there. Let's say it's 6.7. Well, I would have taken this formula that wasn't balanced. I'm going to go ahead and just do this. It would have resulted in okay, so that's my balanced reaction formula. I've got a multiple of 6.7, so now I'm going to take that 6.7 and multiply that, and that, and that by 6.7. We're going to end with 670 grams of calcium plus 6.7 times 52.5. I'm not going to go ahead and try to do that math here, other than 319 grams, just real rough ballpark. 319 grams of nitrogen reacts to produce 1 kilogram of calcium nitride. So what I've done is taken 6.7 times that much to produce that much. 6.7 times that much, tell me that much. And 6.7 times this much to produce that number right there. I'm making 6.7 batches, and each batch makes 152.5 grams for a total of 1 kilogram. Anybody else still writing? Okay. A chemist, number 1, the next, actually the only other one that really has any significant issues. The chemist uses an experiment to decompose 150 grams of water. So it decomposes 150 grams of water. Decomposes the water. What's that mean? What's the chemist doing when they decompose the water? Breaking it down into its constituent elements, right? So they're taking a compound and they're breaking it into atoms. They're taking a molecule and breaking it into atoms. They're taking a compound and breaking it down into its constituent elements. So we're going to end up with some hydrogen and we're going to end up with some oxygen. I can see both those elements in the compound here. But it says they decompose 150 grams of water. And if he finds that he makes 16.7 grams of hydrogen, how much oxygen must have been produced? precise can I get? What's 150 points here? Okay, so I'm going to go to the tens place. Grams. Right. How do I know that? Because the mass of all of this has to equal the mass of all of this. This is 150, and this is 16.7 plus something. What's the something? 133.3. 133.3 plus 16.7 is 150. So we produced 133.3 grams of O2. All right. I look for the nonverbal for feedback, to find out. So when I was that the problem? Was it difficulty understanding the problem, or was it just like a nervous reaction that you had completely detached from the problem on the board? Pardon?
I did it.
Oh, so that was an exaltation. You were like, yes, but it was like modified. Yeah, I got it. Okay, that's cool. The only other one, let's see, 9 and 7, since we have a few moments. Name all the compounds in problem 8. So we look back at problem number 8. Naming a compound. First, what's the first question when you're trying to name something? When you're given the chemical formula and you have to name it, what's the first question you need to ask? The very first question. When you're trying to name a compound and you're given the formula for the compound, what's the very first question that you need to ask?
Is it?
Right. Is it ionic or covalent? Why? Because depending upon whether it's ionic or covalent, you're going to use a different naming system for it. Right? Mm-hmm. So, you have to decide if it's ionic or covalent. In order to determine if it's ionic or covalent, what are you going to go hunt for?
Metals.
Metals. If you find a metal, then it is ionic. If you don't find a metal, then it's covalent. So let's just do that for the first one. C2H6. You find a metal. Okay, so it's covalent, which means we're using prefixes, right? So now we need to go to naming this using the prefixes. The prefixes come from the subscripts. So what is the prefix before this C? Di. So 2 is just di. Then I attach, after the prefix, I attach the element name. It's not the trailing, so it's going to be the element's name. In this case, it's carbon. Dicarbon. Then we go to the next element. Its subscript is 6. Okay. The prefix hexa. Now it's the trailing. It's the last element. The last element. What do we do different about the last element? Both in the ionic and the covalent naming paradigm, the last element always gets a modified name. It gets its IDE name from table 2.1. The IDE name. That's why 2.1, 2.2, and 2.3. Table 2.1 and 2.2 you have to have memorized. Table 2.3 you need to have the bold ones memorized. Because you would have to say 6. 6 is hexa. It's the last element. I get the IDE name of this element. It's hydrogen. Hydrogen's IDE name is hydride. So this is dicarbon hexahydrate. Common name, I think, is ethane. I believe it's ethane.